Hello, welcome to this video on big O as x goes to 0. In another video, we'll look at big O as x goes to infinity. Let's start by considering just the basic polynomial functions y equals x squared, y equals maybe something in between there, x to the 3/2, y equals 2x cubed, y equals x cubed, and y equals x to the 4th. What are we doing with these guys? We're looking at them as x goes to 0. Focus your attention on the origin there. We're looking at the growth rates of the functions. So as x goes to 0, we have the fact that yes, x is larger than x to the 3/2, who is larger than x squared, and so on. True. But how do they approach, what's going on with the functions in the manner in which they approach 0? That's what we want to study. And so because of this fact of this inequality that's here, we can then say that as long as your exponent is larger, then your size will be less than or equal to some constant times the other polynomial term with a smaller exponent. So we're talking about, for instance, x to the 4 is smaller than or equal to x to the 3 as you go towards 0, as x goes towards 0. We can drop the absolute value bars. Everybody is positive here for the ones that we're talking about. And no reason why we have to stop at x, but it's just more visual to stop at x and take a look at these guys. The definition of big O as x goes to 0 is exactly that this inequality is true. C is just going to be some constant. We need that inequality to be true. And then when it is, we say that the function on the left is in big O of the function on the right. And this is going to be true so long as m is greater than or equal to n. When m is equal to n, then yeah, the constant is going to be a 1. But we have an instance here where we have like y equals 2x cubed and y equals x cubed. And so the x cubed is less than or equal to the 2x cubed, which is true as we approach 0. And so the constant, the m and n are equal, and the constant there is a 2. All right, great. So what are we saying? Like, what does this mean? Well, think about limits. We're going to divide one by the other. We can drop the absolute value bars. Everybody's positive here. Just imagine that equation and dividing by x to the n. It is going to 0, but x to the m is also going to 0. And so if this is true, that this inequality is true, then we're going to say that this limit then must be equal to that constant. That constant could be 0. That constant could be 1. We're talking about a finite constant there. So it is true so long as the m is greater than the n. Because what are you going to do with those exponents? You're going to subtract, right? X to the m minus n. Okay, and if m is bigger than n or equal to n, then that's going to be x raised to some positive number, and x is going to 0. So yeah, it's going to be equal to 0 or possibly equal to 1 or whatever. If maybe there's a multiplier there. And so this is a true statement when the previous, inequality holds. So we can view it from many different angles. Here's another way to think about it. X to the m, the bigger guy, bigger exponent, approaches 0 at least as fast as, possibly faster than, the x to the n. Right? X to the 4 approaches 0 at least as fast as x to the 3. X to the 2 approaches 0 at least as fast as x. So when that's the case, we'll have the fact that x to the 4 is big O of x cubed. X to the 2 is big O of x as x goes to 0. All right, great. So let's just get rid of the x to the n's and just talk about in general. For f of x to be in big O of g of x, we need that inequality to be true. For some constant c. I didn't put it here, but yeah, for some finite constant c. And so we do our division. If the functions are positive, we're fine. If they ever are negative, we can just slap absolute value bars around them So there's that the limit that goes along with it. And then the wording, right? Replace the x to the n with the f of x, replace the x to the n with the g of x, and we're having that f of x approaches 0 at least as fast as, maybe faster than, g of x. And then we want to go one step further and talk about Taylor expansion. Okay. When this is the case, when f is in big O of g, then we can say that all of our attention should go to the lowest term in the Taylor expansion, if you're even able to Taylor expand. The lowest term in the Taylor expansion of f has the same degree or a higher degree than the lowest term in the Taylor expansion of g. Okay, we're talking about the terms like, x to the powers on x. The lowest term in the Taylor expansion of f has the same degree or possibly a higher degree than the lowest term in the Taylor expansion of g. And so we have all these different viewpoints. We have a graph. And so when posed with the question, we have many different ways to look at it. We just have to figure out, of these different ways, how can we really be sure? How can we nail down exactly the truth? And so let's look at the questions that were posed on the slide that you saw in the lecture video. Let's look at them in great detail. So the question that's posed is this polynomial 5x plus 3x squared, is it in big O of x squared? Okay, let's pursue this from the limit perspective. When I divide the f by the g, I'm looking at the limit as x goes to 0. You plug a 0 in, right? You'll get 0 over 0. So use L'Hopital's rule. And you trade that in for the limit as x goes to 0, the derivative of the numerator divided by the derivative of the denominator. Plug a 0 in again. And what you're having now, though, is that 5 is the numerator, while the denominator is going towards 0. It's going to be very small. 5 divided by a very small number, like 1 over a billion, it's going to be 5 billion. It's going to be a very large number. The point is that this limit is not a finite constant. So because of that, then, no, can't be true. We need the limit to be a finite constant, like we said, c. So the answer is no. That function, 5x plus 3x squared, is not in big O of x squared. As x goes to 0. All this video is about as x goes to 0. All right, well, how about the other one then? Is 5x plus 3x squared in big O of x? Same viewpoint. Let's go with the limit. Take f over g. Everything's positive. We don't have to worry about the absolute value bars. And L'Hopital's rule again, right? This is 0 over 0 again. Execute L'Hopital's rule. Derivative of the numerator is still 5 plus 6x. Now our derivative of our denominator is a 1. And you plug a 0 into that, and you get a 5, a finite constant. And so, because you got that constant, the answer is yes to that question. Yes, 5x plus 3x squared is in big O of x. Let's take a look at the graph. So the black curve, that's a line. That's actually, it looks like a line, but it's actually, there's more to it. It's a parabola. That's your 5x plus 3x squared. And then we have our x, and then we have our y equals x squared. What are we saying here? We're saying that the rate at which these functions are approaching 0 is similar. Basically, the rate at which y equals x approaches 0 is 1/5 of the rate at which y equals 5x plus 3x squared is approaching 0, that constant there. The 5x plus 3x squared is approaching 0 at a rate 5 times as much as y equal x approaching 0. And so because of that, then we can say, yes, it's in big O of x. Now, let's look at it from the Taylor, actually, you know what, let's try to flip it though. So imagine these limits being reversed, where we look at it like, is x squared in big O of 5x plus 3x squared? If you flip this limit, you'll end up with a constant. You'll take the same, everything will happen. It'll be 0 over 5. It'll be 0. Okay. In the second one, though, when you do that, you'll get 1/5. The whole point is that both of these end up as constants when you reverse the order there. So yes, x squared is in big O of both of them, but x squared is in big O of 5x plus 3x squared, and x is in big O of 5x plus 3x squared. But they're not the other way around. It doesn't work both ways. Okay. All right, great. Let's see the next example. We have sine of x. Is sine of x in big O of x squared? Let's look at the limit perspective. Let's divide. Officially, if you're coming from the other side of 0, sine x does go negative. So officially, there'll be some absolute value bars there, but let's just focus on the right-hand side. 0 over 0, L'Hopital's rule. L'Hopital rule says then, okay, derivative of sine is cosine. X squared derivative is 2x. We'll look at that limit instead. Plug the 0 in there. Numerator is going to 1. Cosine of 0 is a 1. Denominator is going to 0. It's going to get very small. So it's the same action that happened before. The 1 divided by a very small number is a very large number, and so it won't be a finite constant. Therefore, no, it can't be that sine x is in big O of x squared. All right, what about big O of x? Same thing, but now we're going to do sine x over x. This is a famous limit. This limit is 1. We'll just do it by L'Hopital's rule. Plug a 0 in, you get 0 over 0. And then we take the derivative of the numerator, which is cosine x. Derivative of the denominator is now a 1. So we're looking at this limit being equal to 1. They approach at the same rate. The graphs should be approaching 0 at the same rate. Okay, let's take a look at those graphs. The red graph is y equals x. The black graph is y equals the sine of x. Notice how they're approaching 0 identically at the same rate. It's not like before we had the 5 and the 1, the rate at which they were approaching. This guy is approaching at the same rate as, it's essentially on top of the other function. The constant was a 1, not a 5. Any other guy is just your y equals x squared. Okay. It's a different rate. Okay. And so let's go to the expansion, right? So the Taylor expansion for sine of x is x plus x cubed over 3 factorial, x fifth over 5 factorial, and it keeps on going. The HOT stands for higher ordered terms. And so you focus your attention on the lowest, the first power, the lowest exponent. The degree of that lowest exponent is x. It's to the 1. That's the first degree. So you are for sure big O of x. The degree of the lowest power on x is equal to x. But it wouldn't be, if it had been an x squared there, we could say, yeah, we're in big O of x squared. So we can look at it in many different viewpoints, limits, graphs, Taylor expansion, whatever we need to be sure to say, yes, it's in big O of g, or no, it's not in big O of g. All right, great. Let's keep this going. The lowest term in the Taylor expansion of sine x has the same degree as the lowest term in the Taylor expansion of x, which is just x itself. All right, we're doing great. Let's keep this going. Natural log of 1 plus x, take away x. Is that in big O of x cubed? Is it in big O of x squared? Let's approach this from the Taylor expansion route. So what is the Taylor expansion for natural log of 1 plus x? It's one of the list of 7 or 8 guys who we need to know the Taylor expansion of. It comes from taking the geometric series, making it alternating by, instead of having 1 over 1 minus x, having 1 over 1 plus x, and then it comes from integrating that. You end up with this guy here, x minus x squared over 2 plus x cubed over 3, and it goes on forever in all directions. And it has higher order terms, okay? And what we want to do is take away x from that. So let's take away x from both sides. And our leading term, the lowest power term, is x squared. Okay, so with that, we can immediately say no to the first question and yes to the second question. The lowest term in the Taylor expansion of natural log of 1 plus x minus x has the same degree as the lowest term in the Taylor expansion of x squared. They match. The limit would be a half there. If we divided ln x minus x by x squared, our limit would be a half. That would be our constant. But if we divide it by x cubed, we end up with a non-finite constant as the limit. So no to the being in O of x cubed and yes to being in O of x squared. And there's the graph. Doesn't really illuminate too much for us, but there's the y equals x squared, and the black is the. I had to put absolute values bars around it because the function natural log of 1 plus x minus x is actually below the x. The y value is negative as you end up approaching 0. And then the other guy is just y equals x cubed. All right, this video is getting a little long, but that's okay. I want to make it one video all about big O of big O notation as x goes to 0. I want to have just one video about it. All right, let's keep it going then. 1 minus cosine of x squared. Is that in big O of x to the 5th? Is it in big O of x to the 4th? How are we going to do it? Taylor expansion. We know the cosine of x expansion. So what about the cosine of x squared? Replace all the x's with x squared. X squared squared is x to the 4th. X squared to the 4th is x to the 8th. Higher order terms. Okay. What we want is 1 minus this. 1 minus the cosine of x squared. So we apply the minus to all terms. The ones cancel out. We end up with x to the 4th as our leading term over 2 factorial. And x to the 8th over 4 factorial with a negative on it. And it keeps on going for higher order terms. So we focus on that lowest term. The lowest term in the Taylor expansion of 1 minus the cosine of x squared has the same degree as the lowest term in the Taylor expansion of x to the 4th. You are in big O of x to the 4th. You are not in big O of x to the 5th. All right, great. One more. We have e to the negative 1 over x squared. Is this in big O of x to the n for all n? Does this function approach 0 at least as fast as x to the n? Does it approach 0 faster than x to the n? That's the question we want to answer. And so that inequality, does it hold? Is that inequality true? Is the f of x less than or equal to the constant times the g of x? I didn't put absolute value bars around the e because it'll always be positive. X to the n, I guess if you're, depends, but if you're coming from the other side, it's possible that if you're plugging in negative values of x, you got to be careful, whether this n can be a root or not. But anyway, is this true? Is this true for all n? Let's go with integer n, basically. Positive integer n. And so if it is true, then we want to see what are the ramifications of it. Like let's assume it is true. Okay, and let's see if we violate anything. If it's true, then we can take the natural log of both sides. Natural log of the left, natural log of the right. In doing that, then we'd have the ln of e to the negative 1 over x squared. On the right hand side, we'll have the ln of c times the absolute value of x to the n. Subtle thing I did there. The absolute value of x to the n is equal to the absolute value of x, the entire thing raised to the n. It's multiplicative like that. And so the log on the right-hand side is a product. It can break it into 2 separate logs. And c is a positive constant. And so we could drop that part off and say basically that on the left-hand side, the ln and the e cancel. We'll have negative 1 over x squared. On the right-hand side, we could use the log property and bring the n down in front. The log of c, if you are, that log of c is some positive, we can drop that off and say, yes, we're also lower than this. And so what does this mean, though? That negative 1 over x squared is less than or equal to n times the natural log of x. Well, we're going to do some creative multiplying here. We're going to put the n, multiply by 1 over n, but divide both sides by n. Multiply both sides by a negative x squared, so that we have 1 over n on the left. Now the inequality is going to flip signs. It's going to be now negative x squared log x, but then it's going to be greater than or equal to there. Is this true for all n? Basically, if any of these statements are true, we can be able to, as long as we, these are legal reversible steps here, we can then say, yes, that original statement is true. So yes, it is in big O of x to the n for all n. And so negative x squared log x. And remember, whole thing is x is headed to 0, right? So let's look at that limit. X is headed to 0, negative x squared times the natural log of x. that's of the form of a zero, a function headed towards zero times a function headed towards infinity or negative infinity. So we we have a product that's indeterminate. We can make it a fraction and end up with a form that's usable as far as L'Hopital's rule goes. So instead of multiplying by x squared, we divide by 1 over x squared. We didn't change anything. It's still, if you multiply by the reciprocal, you're back where you started at. So we have then a infinity over infinity limit. So we can apply L'Hopital's rule, take the derivative of the numerator, divide it by the derivative of the denominator, do a little bit of algebra, and we'll see that this limit is 0. So what we're saying is that as x goes to 0, then what's going to happen is, yes, this is a true. 1 over n is definitely greater than or equal to 0. We're talking about, for all n being, these powers on x. And so all of these steps are reversible. So we come back with the answer, yeah, because if this is always true for n, all the other steps can be reversed. Yes, it is true that the inequality holds. Yes, it is true that e to the negative 1 over x squared is in big O of x to the n. If you look at the graph, I mean, you could even like play around with the numbers, like, if x is some number very, very close to 0, and compare it, compare like the fraction, right, the f over g. What you'll see is that the numerator is going to be something that is smaller than the denominator. And if you happen to see that the numerator is bigger than the denominator, all you need to do is get closer to 0, and you'll see that it'll flip-flop. This function goes to 0 very rapidly, exponentially. It goes to 0, so it's going to grow to 0 faster than any kind of a polynomial term, basically. And so that's it. So we went through many different ways to view big O as x goes to 0. In the next video, we'll go through many different ways to view big O as x goes to infinity. All right, thank you for watching. My daughter says I should say like and subscribe, comment down below, and I'll see you in the next video. All right, take care.